Okay, welcome to another Root Labs session. Today we have Toon on interactive clustering. Toon is a machine learning engineer at DataRoots. He is on his PhD on semi-supervised clustering at DTAI at Leuven. And on today's content of the webinar, he wrote a paper for which he received an award at the Discovery Science in 2018. If you have any questions, they can be posted in the Q&A section here in Zoom, and we will visit these at the end of the webinar. The session is recorded and it will also be posted on our YouTube channel. So yeah, it's over to you, Toon.
Okay, thank you, Bert. So I will talk about clustering and more specifically how to make it easier by making it interactive. So clustering, as most of you probably know, is the task of finding structure in data by identifying groups of instances that are highly similar. It's a key task in data analysis with applications in a very broad range of domains. For example, you can use it to do market segmentation, player scouting, gene expression analysis, and so on. Basically, every domain where you have data and you want to obtain some insights into that data, clustering might be a useful tool for you. It's also important to note that clustering is inherently ill-defined. It's an unsupervised problem, so we do not have a clearly defined loss function or performance metric that we want to optimize. So this is also what makes clustering challenging. I would say that the typical clustering workflow looks more or less as follows. So you have data that you want to cluster. You have to choose a similarity measure, a clustering algorithm, and also set hyperparameters for that algorithm. And once you have done all that, you can look at the clustering and decide whether you find it satisfactory or not. Typically, you will not be satisfied with what you get on your first try. So you have to go back to the components in this clustering pipeline to try to make some different choices to get a better clustering. So you can try a different similarity measure, or you can try a different clustering algorithm, because it's well known that all these algorithms make very different assumptions on what clustering structure in the data is exactly, so they can give you very different clusterings. And you can also try to, of course, change the hyperparameters because they strongly impact the clustering that you get. Once you made a couple of new choices, you again get a clustering and you repeat this process until you are happy with the result that you see. So typically it takes quite some iterations until you get to a satisfactory result. And this is a tedious and difficult process because you have to have a lot of expert knowledge on clustering, right? You have to know how similarity measures work, how the clustering algorithms work and what their assumptions about the data are, how the hyperparameters affect the clustering that you get, and so on. So this is a tedious process. Of course, in an ideal world, our clustering process would be much simpler and would just look like this. We would give our data to a black box clustering system. We don't have to know how that works, and we get a clustering return that we find interesting. But because clustering is inherently subjective, such a black box clustering system cannot work. It often depends on your goals, your interests, your background knowledge, which clustering that you actually want to see for a particular data set. So there are often multiple valid clusterings for a single data set, and without any interaction, the clustering system cannot possibly know what clustering we would like to see. To really stress this point that clustering is inherently subjective, I have this toy data set here of a couple of animals. And if I ask you to cluster this data, some of you might say, well, I'm going to group the mammals together in one cluster and the reptiles in the second cluster, which is a perfectly fine clustering, but some might choose a very different clustering. For example, by grouping the land animals in one cluster and the semi-aquatic animals in the second cluster. So both solutions are, of course, correct or valid. It just depends on what you're interested in. A bit more practical example, maybe suppose you have data describing persons, for example, with their age, their gender, their education history, job history, spending patterns, whatever data you can have on persons. If you now are a market researcher that is looking for groups of people that are more likely to buy a certain car, you will be interested in very different clustering than, for example, a medical researcher that is interested in finding groups of people that are at higher risk for a certain disease. So it really depends on your goals, on your interest, what clustering that you would like to see for a certain data set. So this is a motivation to go to the following interactive clustering workflow. So we do need to have some form of interaction with the clustering system. And in the typical unsupervised clustering workflow, this was through setting hyperparameters in the clustering algorithm or choosing different algorithms and so on. But this was quite tedious. So this is an alternative workflow, let's say. So here we give our data to a semi-supervised clustering system, which is as black box as possible. So preferably we don't have to know how this clustering system works. This system gives us a clustering that we can inspect, and we can again decide, do we find it satisfactory or not? Now, if we do not find it satisfactory, the clustering system will query us, the user, through the form of pairwise queries. For example, here, this one example for the pairwise query, in the example of the animals that we could group. So the clustering system might ask us, should the monkey and the lizard be in the same cluster? If we answer yes, we give a must link constraint. If we answer no, we give a cannot link constraint. So the system might ask a couple of these questions. This results in constraints, and these constraints can help the semi-supervised clustering system to find better clusterings. So after answering a couple of pairwise queries, we get a new clustering. We can again decide whether we find it satisfactory or not. If not, we just answer some more questions and so on until we're happy with the result that we see. So the advantage of this workflow would be that we can answer these simple pairwise queries, which only require us to have domain knowledge, and we don't need to do this tedious tuning of hyperparameters and selecting the appropriate clustering algorithm for our data and so on. So this is the workflow that we would want to go to in this presentation. This clustering in the presence of constraints has actually been studied for quite a long time already, and many semi-supervised clustering algorithms have been developed. Typically, they are then developed as extensions of existing unsupervised algorithms. For example, for k-means, we have COB k-means, MPC k-means, and so on. The same for spectral clustering, we have several semi-supervised variants. For dbScan, basically for all the major clustering algorithms, the popular clustering algorithms, there are several semi-supervised extensions that can work with these pairwise constraints. So that's good, but they typically do not really allow for the interactive workflow that I was describing before. So these existing algorithms typically assume, of course, that the data is given as inputs, but also that all the constraints are defined beforehand. So given data and constraints, they try to find a clustering that satisfies these constraints. This is not exactly the same as what I described before, where it's really a more iterative and interactive process where the clustering system can give you an intermediate clustering. You can answer just a couple of pairwise constraints, not a lot of them, and then you again get a new intermediate result. So well, there are many semi-supervised algorithms that already use pairwise constraints. None of them really satisfied the workflow that I described before, which was a motivation to develop COBRA and COBRAS, two clustering methods that I will describe now in the remainder of the presentation. And so these methods can be used in this workflow. So I will describe COBRA and its successor COBRAS based on this toy example of some time series. And again, here for this data set that we will cluster, there are at least two possible clusterings that we might get. Some might say, well, I'm gonna group the monotonous instances into one cluster and the non-monotonous instances in the second cluster. And someone else might say, well, I'm gonna group the smooth instances into one cluster and the non-smooth instances into a second cluster. So both are fine. In this example, in which I will illustrate COBRA, I will first assume that I will want to group the monotonous instances together and the non-monotonous instances. So now I'll briefly describe the basic idea of COBRA. It's two simple steps. In the first step, we will overcluster the data to create what we call super instances. And with overclustering, I just mean running a clustering algorithm with a number of clusters that we expect is too large for this data set. So for this toy data set, for example, I created 4 super instances here, but in a practical example, this would be probably a lot more. Each of the small clusters that we get in this way, we refer to as a super instance, and that's basically the building block for the clusters that we will construct in the second step. So the second step consists of merging these super instances into clusters. We'll also illustrate this with this example. So we'll first look at the two super instances on the left, and the question is, well, should they be merged to a partial cluster? In this case, we check this by checking the pairwise relation between this instance over here and this one over here. They're both non-monotonous, so we would say yes, they should be clustered together. We answer with a must link, a green line, and we have a partial cluster on the left. We repeat this also for the two super instances on the right. We answer with a must link because they were both monotonous, and we have a partial cluster on the right. Now we still have to determine whether these two, at this moment, partial clusters should still be merged together. So we also have to query the pairwise relation between, for example, this instance over here and this one over here. But now it's a non-monotonous instance and a monotonous one. So we answer with a cannot link, and our clustering is done. We have two clusters. From these three pairwise constraints that we have, we can derive all the other pairwise constraints between the super instances. So we know all the relations we need to know. Our clustering is finished at this moment. So this is the COBRA clustering procedure, the basic idea behind the COBRA clustering procedure. Okay, so this works, but it has an obvious problem, right? So the first step of COBRA is to just generate a number of super instances, which immediately raises the question, well, how many super instances should we generate? If we generate a lot of them, we will probably get to a good clustering, but we will have to answer a lot of pairwise queries before we get there. If we generate too little, then we might have super instances with a mixture of instances that actually should not be clustered together. For example, for the 4 super instances that I had before, if I was clustering based on monotonicity, this was fine. But if I now want to cluster based on smoothness, we would never get a good clustering because here are 2 non-smooth instances, but also 2 smooth instances. So that's a problem. And that's also the motivation then for now the successor, which we refer to as COBRAS. So I will illustrate this procedure on the same toy dataset. And in the initial situation in COBRAS, we just have one big super instance, and this is part of its own cluster. And now the first task, of course, will be to split this super instance into several smaller ones. And then we have to ask, well, how many new super instances should we create? And this time we will also answer this question by using pairwise constraints. So to know how many super instances we create, we follow the following procedure. We first split this big super instance into 2 smaller ones, and we query the pairwise relation between the 2 newly created super instances. So in this case, we do it by querying the relation between this instance over here and this one over here. And now for this example, so before in the COBRA example, I was clustering based on monotonicity, but now I will cluster based on smoothness. So this is a smooth instance, and this is a non-smooth instance. So there's a red line, it's a cannot link. So we know that we have to split this one at least once, otherwise we would be mixing instances that should not go together. Now the question is, of course, should we split even further? To answer that, we do exactly the same thing, but now to this super instance on the left. So we split it further into 2 smaller ones, and we query the pairwise relation between the resulting super instances. In this case, we have a smooth instance over here and a non-smooth instance over here. So it's again a cannot link. So we know that we have to split this one at least twice to get to a good level of granularity. Again, the question is, should we split even further? So we do the same. And at this point, we get 2 very small super instances. They both contain a smooth instance. So we have a must-link constraint. So we know, well, that this actually might be a good level of granularity. We will not check this level for the right branch. We will just assume that it will that this splitting level is also appropriate for the right branch, which means that we will split this super instance here into 4 new ones. So this brings us to the following intermediate situation. So we now have 4 super instances, each part of their own partial cluster, and this is the starting point for a COBRA merging step. So this is exactly the same procedure as I discussed before. I'm going to skip through it. And this brings us to the following first intermediate clustering. So we have here on the bottom already nicely a pure cluster with only smooth instances. And on the top, we have a cluster that mostly contains non-smooth instances, but also still contains smooth instances in this super instance over here. So this clustering is definitely not finished yet. Now in COBRAS, that is not a problem because we will basically repeat the 2 steps that I did before, but now to this larger super instance over here. So we repeat the same steps. We will first split the super instance into smaller ones and then merge the newly created super instances to existing clustering structure. So in this case, we're going to split this one. We again have to wonder, well, how many new super instances should we create? So we split it into smaller ones and query the pairwise relation. It's a non-smooth and a smooth instance, so it's a cannot link. So we try to split further. At this point, we see that we have a non-smooth and a non-smooth instance. So we're going to split this super instance here into 2 new ones. This brings us to the following intermediate situation where we have the 2 newly created super instances. And this is again the starting point for a new merging step. So we are going to create the relation of these newly created super instances to the existing clustering structure. So that follows the same principle as before. And after answering a couple of pairwise queries, we see that we now have the clustering that we were looking for, right? The bottom cluster only contains smooth instances and the top cluster only contains non-smooth instances. So this is the idea behind COBRAS. Now to demonstrate that this can be used really to follow this interactive workflow that I described before, we also made a small web application that can be used, for example, to cluster time series of images. So I'm gonna briefly run through an illustration of this interactive clustering process, first for time series and then very briefly for images as well. So for the time series data, well, this is actually the data set that I will cluster. So it's a CBF data set, it's publicly available. And here in this image, I just plot all the time series on top of each other. So it's not terribly informative, but just to give you an idea of what the data set looks like. And if you go through this data set, you will very quickly find that there are at least 3 patterns that you can distinguish. There are downward patterns, there are horizontal patterns, and there are upward patterns. And actually, you might also want to obtain other clusterings of this data set, but we are now trying to cluster just into these 3 groups. So we want 1 cluster with downward, 1 with horizontal, and 1 with upward patterns. And for us, that is very easily to make the distinction between these 3. But actually, if you try to cluster this data set with existing clustering algorithms that are tailored for time series, it's not that easy to get this result. For example, with constrained dynamic time warping with semi-supervision, if you ask for 3 clusters, you get the following result, basically a mixture of patterns in each cluster. So definitely not what you want. If we cluster it with K-shape, which is another very nice time series clustering algorithm, we get a better result, but still a mixture of horizontal and downward patterns in the 3rd cluster. So it's not exactly the result that we're looking for. So now I'll illustrate how we can cluster this data also with COBRAS. But before we do that, I still want to make the remark that, well, now we are using time series data. So we will not use a standard Euclidean distance, but distance measure that is more appropriate, namely the dynamic time warping distance. If you're not familiar with this dynamic time warping distance, it's very briefly illustrated here in the figure. If we have the red time series and the blue time series, well, for most purposes, we would consider them to be very similar, right? They have the same shape here. It's only that it is shifted a bit. And an Euclidean distance cannot really cope with this shift, but then dynamic time warping can basically map these points to handle this shift. So the dynamic time warping distance between these 2 instances would be low, as you would intuitively expect. So we are running COBRAS now with the dynamic time warping distance. So the interface looks as follows. We have here the data set that I already showed before, the CBF data set. Here on the right, we have this querying interface. So we simply have to answer these pairwise queries here. And on the bottom, we have the intermediate clustering. So with COBRAS, in the beginning, there is only one cluster. So, well, it's the same image as above. But so now we will answer a couple of these pairwise queries. For example, here, it's clearly a must link because they are both horizontal. We get a second query. We have a downward pattern and an upward pattern. We answer cannot link because they should not go together. And after two queries, we get our first intermediate clustering. We see here on the left a cluster that looks already relatively pure, so it's mostly upward patterns. On the right, it's clearly a mixture between downward and horizontal patterns. So we're not happy yet with the clustering that we see. It's not really a problem. We can just tell the system to give us some more pairwise queries, and it will present us with a couple new ones. So I'm gonna go through this. It's very easy to answer these queries. And after 7 pairwise queries, in this case, we get the following intermediate clustering. And it's also, I think, the final clustering because this one looks good, right? We have here on the left the upward patterns, then in the middle the horizontal patterns, and then the downward patterns. So this is meant as an illustration to see, to show how easy it can be to kind of steer the clustering algorithm in the right direction. Of course, with the unsupervised algorithms and with proper pre-processing, maybe with a lot of tuning and trying different algorithms, you might also get to this clustering, just as a demonstration of how easy it can be to kind of steer the COBRAS clustering system in the right direction by just answering a couple of pairwise queries. So this was a first illustration of this interactive clustering workflow. I'm now going to briefly also discuss a second one. And for that, we're going back to the example that I used in the beginning of the presentation to motivate that clustering is really subjective, where we had the animals data set. And I said, well, some might want to cluster this based on whether the animals are reptiles or mammals. And some others might cluster the data set based on whether they are land animals or semi-aquatic animals. So we can also actually, well, illustrate this with images, in this case, obtained from the ImageNet database. So we are going to cluster a sample of this database. I show some example images over here, of course, only a sample of the images that we're actually going to cluster. And then I also want to highlight in this case, we're not going to cluster the raw image, the raw pixel values. We're going to cluster based on features extracted using a pre-trained inception network. So, of course, we want the semi-supervised clustering system to be as black box as possible, but still we have to make some sensible decisions here about how to represent our images. The same was true with the time series clustering example. There we still had to choose a sensible distance metric. So we still have to make some informed decisions, but with these things in place, I hope that these examples illustrate that we can more easily get to a good clustering. I'll also illustrate it now very briefly for the image clustering example. So I skipped through the query answering part here. It's the same interface. You get 2 images and you have to answer whether they should be in the same cluster or not. And so for the first clustering that you might want to get, which was based on, well, grouping the semi-aquatic animals in one cluster and the land animals in the second cluster, well, this clustering we can get with COBRAS after answering 2 queries. So here we see a sample of images from the first cluster, and here we see a sample of images from the second cluster. Now, to be fair, this would also probably be the clustering that you get with k-means if you just ask for 2 clusters. So k-means, just running standard k-means with 2 clusters would give you this solution. Now, the question is, of course, if you would be interested in the other clustering, grouping reptiles in one cluster and the mammals in the second cluster, the question would then be, well, how can we get this clustering from k-means or another unsupervised clustering algorithm? So maybe with some tuning of the distance measure or with trying various clustering algorithms and hyperparameter settings, eventually we would get there, but I'm very certain that it would be, well, a tedious process. And now if we do this with COBRAS, if we answer again 7 pairwise queries, we see that we can very easily get here on the left a cluster that only contains mammals, and on the right a cluster that only contains reptiles. So both clusterings are very easy to obtain with this interactive clustering process. So that concludes also the second illustration that I wanted to give. So to wrap up this presentation, I started by, well, giving the motivation for this work, which is that clustering can be very tedious. You have to have a lot of knowledge about metrics, clustering algorithms, parameter settings, and typically you need quite some iterations to get to a good result with this typical unsupervised clustering workflow. I hope that I illustrated with COBRA and COBRAS that you can much easier get to good clusterings by only giving a very limited amount of user feedback. So of course, this does not make the entire clustering system a black box. You still need to think about some things. For example, for the time series, it was useful to use a dynamic time warping distance. And for the images, we had to use an appropriate feature representation. But I still think with these things in place and COBRAS on top of that, it was much easier to get to the clusterings that we want. If you want to read more about this, much more information can be found on this URL over here. So this was work that I did while I was at the DTI in KU Leuven. And if you want to try this yourself, this code for this is on pairwise, so you can easily install it with pip command. And with that, I conclude. Thanks for watching.
Thank you, Toon. We have a question. We have a question from Hassan, who's asking, it's fine for two-dimensional data, but how about more than 3D data that we cannot illustrate?
So I am assuming here, so the data in itself can be from higher dimensions. For example, the images, the feature representation there is a 2048 number vector, but we just display then the corresponding images. So as long as you can visualize your data, should be fine, and the dimensions do not matter. For example, time series would be a good example. The images, if you cluster documents, you can have a high dimensional representation of your document, but you can just display the document. If you just have purely numerical data, with just like the standard attribute value data, then to use this thing, you're basically counting on the fact that you probably have some additional domain knowledge about the data that you're describing through these feature vectors. These feature vectors might, for example, describe certain machines, and you might have some extra knowledge about these machines that's not captured in the features that you can use to answer these pairwise queries. But so it's not a coincidence that in the examples here, I've chosen time series, which are nice to visualize, and images, which are also nice to visualize. So that helps, certainly.
Okay. Another question is, can you have contradictory constraints? So, and if so, how would you deal with these? An example is A and C must link, B and C must link, but A and B must not link.
Here we assume that this is not possible. So this assumes that you always are able to answer these pairwise questions. Now there is follow-up work on this that is able to deal with this. So it's a paper that we're currently in the process of publishing, where you, well, in some cases, you might not be able to answer all questions correctly. There might be some noise on the queries. So there is an extension for this. I don't know if the code is made publicly available yet, but we are working on this. Well, not me anymore, but my former colleagues are trying to deal with that. So it will hopefully soon be public, but in this version that I presented here, we assume that all queries can just be answered correctly.
Okay. Another question from Ashish. Apart from ease in clustering, how does COBRAS perform compared to classic clustering algorithms?
So if you really just look at the quality of the clusterings you get compared to classic clustering algorithms, typically you get much higher quality clusterings in a lot of cases by just giving a few pairwise constraints. So in like the typical benchmarks we do in the paper, yeah, your quality of the clustering improves a lot compared to unsupervised benchmarks. In a sense, it's also not really a fair comparison, of course, because well, we have extra information that we can use, but it shows that this extra information is really helpful. So, yeah.
Yeah. Okay. And those were the questions, Toon. Okay. Thank you for presenting interactive clustering. Really interesting. Thank you all for joining. And we have a next Root Lab session next week on building a data lake in less than 1 hour. Okay. Thank you. Bye.